As you can imagine, the fundamental theorem of calculus is a big part of this course, and we need to talk about it a little bit more. We've worked on it with the idea of f of b minus f of a equals the integral from a to b of f prime, and we've also worked on it with what happens when you derive an accumulation function. Okay? But let's build off of it a little bit more. You just had the chance to answer a question regarding water in the pool. All right? What if we could come up with an equation that describes how much water is in that pool? Well, the fundamental theorem of calculus basically allows us to do that. So you see there's some space in your notes there. Watch this change that we're going to make. All right? If I had asked you, how can we get f of b all by itself? What would you do to both sides in order to get f of b to be all by itself in this equation? Yeah, you'd add f of a. So let's do that. If we add f of a to both sides, we're going to have f of b is equal to f of a plus the integral from a to b of f prime of t dt. And I know we're used to seeing x there. I'm using t there for a reason, which you'll see in a moment. Okay. Well, we now have f of b all by itself. But what if we don't want f just specifically at a value? What if we want f in general? Well, we'd have to change that b to an x, right? If we have f of x here, that's just a function in general. But if we change the b on this side to an x, well, then we're going to have to change the b on this side to an x as well. And when we do that, we end up with f of a plus the integral from a to x of f prime of t dt. The reason why I have these t's here is because I can't use x because x belongs to this function. It's being used as a bound of the integral. So when we have a second variable, we need a second letter. So the common variable to use is t, but can be something else. All right. But more importantly, this right here is an equation for f. We now have the blueprint for how to write an equation for any function. We just need two things. Right? The first thing we need is this f of a. F of a, that's our initial condition. Go back to the pool problem. How much water was in the pool at the start of the problem? Yeah, you needed that value in order to come up with your final answer. So the first thing that we need is an initial condition. All right? And that's this f of a right there. Let me grab another marker. All right, the initial condition, that's our f of a. Okay, if we have that, and we have this second part, which we'll talk about more in a second, then we have the ability to write any function. Right? So what is this second part? Well, that is all the change that's added up. When you got the new value of the amount of water in the pool, didn't you add in all the water that was coming in through the hose and subtract all the water that left through the splashing and evaporation? Okay, so you were taking both of those rates and you were adding up the total to get a total rate of change. That's what we're talking about right there. Right? That's a sum. That means we're getting a total. So we're going to need the initial condition, but we also need the total change from the time of the initial condition. I'm just going to write IC for initial condition right there. Okay? This A matches with that A right there. This is the time at the start of the pool party. This is the time at the beginning of, when we're looking at the population on an island, all right? This is the population at the start. This is the amount of water at the start. This is the time that we're looking at this population or at this amount of water in the pool, all right? So this is our second item. And if we have that, we have our derivative. If we have our rate of change, which is our f prime, if we have that and we have our initial condition, then we have the ability to write an equation for every single function that provides us with that information.